Hello, this is Professor Sultana Nahar from the Astronomy Department of the Ohio State University. I'm very pleased to meet you all. Thanks to your teacher. I'd like to say I'm an atomic astrophysicist. It means I study atomic processes that involve light or the photons in the astronomical objects. Photons are unit of light. We gain our knowledge about stars and galaxies by studying the light, that is the photons, they reach us from there. So today all of us will become atomic astrophysicists during the class, and we'll solve a couple of atomic astrophysics problem. Okay, let me share my screen. This one and share, and I need to make it slide mode. Blue slide. All right. I have to stop it. Okay. So as I mentioned, we study the universe through the light that we catch from them. So this particular picture shows the hydrogen cloud of galaxy M33. You know that 99% matter in the universe is hydrogen. The light we see in stars, galaxies, are created largely by various kinds of atoms in them, and of course, including hydrogen. And the photon is a unit of light. And when a star light passes through the telescopes, either in space or on ground, it is captured by the telescope spectrometer and produces lines, which we see, which we call the spectrum of the light. The particular unique thing about a spectrum that each line corresponds to a particular energy photon. So from detecting the energy of the photon corresponding to that line, we can identify the element in the astronomical object. So today we'll talk about hydrogen. Okay, sorry. So how do the radiation are created? How the radiation created in the atom. So say this is an atom. So this explains that. Okay, this is an atom which has a nucleus of protons and neutrons, and electrons are various orbits. These orbits are fixed. They have fixed energy. They cannot be in between them. So that is why we call the orbits and the energies are quantized. So in physics, we call them energy levels. So for example, when all these electrons are orbiting in their own permanent orbit, then we call it in the ground state or the ground level, the lowest energy. But if one of the electron jumps to a higher orbit, in between higher orbit, then we call it excited state or excited electron or excited atom. And the energy will be different. So probably it will be, that will be the next energy and so forth. If it goes to electrons, they start going to different orbits. So we can have different kind of energies. So typically the outer electron jumps to a higher orbit by gaining energy, which is called excitation of the electron or the atom. The electron can gain energy by absorbing a passing by photon, that is, or it can gain energy from the collision with another electron or atom or molecule, or if it is excited due to the heat around it, high temperature, it can go to an excited level. But what will happen, even it cannot stay in the excited state for a long time. It has to come down. So either to a lower or its own orbit. So when it comes down, what happens to the extra energy it had? It will give out that extra energy in terms of a photon. And that's the photon that we detect through a telescope to study the atom. Okay, so our project is the photons of hydrogen, of a hydrogen atom. The hydrogen atom is the simplest atom. It has a proton and one electron going around it. So when it is in its own permanent orbit, it is in the ground level. In the ground, we say ground state. If it jumps to a different orbit, we can have all kinds of energy levels. So these levels show the energy diagram for hydrogen. So how do you identify a hydrogen atom? By detecting the photon it gives out during the excitation. So electron will go out. So that is happening all the time in the astronomical objects. The electrons get excited, they give out photon, which we capture to study them. So problem one. So we have, consider that we have a number of hydrogen atoms in a star where they are being excited to all levels up to 5. So, okay, excited to level 1, 2, 3, 4, 5. So they are being excited up to level 5. Show that the number of different types of hydrogen photons, different types of hydrogen photons means different energy hydrogen atoms that will come out from the star through the excitation should be equal to n times n minus 1 divided by 2. This is the formula, where n is the total number of levels. So at this time, we are considering 5 levels. So you can calculate how many types of photons can come out using this formula, but you need to also show that they are actually so count how many photons will correspond to the electron coming down from a higher level to the ground level, or the lowest level, which we call Lyman photons. And how many will come down from higher levels to level number 2? We call them Balmer photons, and so forth. So count them, all of them, all possible photons coming out from the star within, when electrons are excited up to level 5. And you know the answer, and you can solve it very easily. All right. The second problem. So we got all kinds of photons, but we want to know the energy of the photons, because that is what we measure in the telescope, and that is what we use to identify the element. So how do we calculate the energy of the photon? Using this formula. Okay, it's called Rydberg formula. Is the delta E means the energy difference between two levels, n and n prime. So n is, it can be the lowest level, and n prime, or any excited level, and n prime is the upper level, from where the electron is dropping down to and giving out that photon. And this equals 1 over lambda. Lambda is the wavelength of the photon. That is what we measure in the telescope. And that is given by this formula, Rydberg formula. This is just a constant. It is given by 1 over 912. Okay, and you have to put the numbers. N is the lower level and prime is the upper level. So using this formula, you are supposed to show that the wavelength of the first Lyman photon means the lower level is always 1, n equals 1, okay, is 1216 angstrom. And that of the last photon, that means coming from infinite level, so n can be infinity, it will be 912 angstrom. So this is your second problem. So you know what to expect when you see an object in the space, and if you see photons coming on and you detect, you can tell that, okay, this is hydrogen and these are Lyman photons or Balmer photons. Okay, you can get many types of photons for each n, that means lower level, but varying n prime. So upper level can be different one, and they form different kind of series. The first one is called Lyman series, when N is 1, the lower level is 1, the first one, the lowest one. Bomber series when the lower level is 2, and Passion series when the lower level is 3. So these series are seen in this hydrogen spectrum below. So all these photons form the lines, So this is like Lyman photons, Balmer photons, Passion photons, and so forth. So each lines correspond to a particular energy photons. So now you have become an atomic astrophysicist, and you can do spectroscopy to detect enough photons and identify them. Okay, thank you. Okay, now to find the okay, here. Stop recording. Thank you and wish you all the best.